So it's a pleasure to introduce the last speaker of the day, Charlotte Chan. She's talking about geometrical packets of T-unramified regular supercuspidals.
Thank you very much for the invitation. So I'm going to take a page of Jessica's book and request that if you don't mind to please turn on your video. Thanks so much. It's so pleasant to see everyone. Monitor. Okay, so yeah, and also as a few people in previous talks have done, I will try to monitor the chat, but I don't know how successful I'll be. So if you have a question, then you can type it there, and then hopefully at some point I will get to it. Yeah, so what I'd like to talk about today is a geometric counterpart to the story of representations of p-adic groups that we saw in Jessica's amazing talk yesterday morning. One part of this will involve a kind of generalization of classical Deligne-Lustig varieties, and classical Deligne-Lustig varieties are something that we've seen already in several other talks, not just as the so-called depth zero input in use construction, as Jessica talked about, but also, for instance, in Bao's talk and Brandon's talk, and likely others that as well. So, so the work that I will speak about today is joint work with Masao Oi, and it's based on a geometric construction that I had previously studied with Alexander Ivanov. So let me start with, so this is my, this is a pretty standard notation. Yes, so, and all my representations throughout will be over C. I mean, there will be cohomology, so then it'll be actually over QL bar, but then we can just take a, choose an isomorphism between the two. Okay, so the picture that I like to think about begins like this, which is that if I take a finite group of Lie type, something like GLN-FQ or SE4-FQ, or and you know, any of these reductive groups over FQ, it's not known how to, in general, construct the irreducible representations of that group. If you want to understand what those representations are, what you must do is look at the cohomology of Deligne-Lustig varieties. And what we saw in Jessica's talk is that what you can do, is there's you can construct, you can build a supercuspidal by a two-step process. So you take as this depth zero input this geometric data, and you supplement it with this pretty involved algebraic construction. And so that's this step one right here. This is step one. And this is the step that had this row K that Jessica had. And then step two is to build the supercuspidal from this using compact induction. So that's this step two. So this is the algebraic picture. But actually over here, there's like lots and lots of stuff, especially motivated by number theory. I mean, perhaps number theory interest in this box was sparked with the work of Harris-Taylor, proving the local Langlands conjecture for GLN via the cohomology of Lubin-Tate space, and but that was kind of just the beginning. So since then, people have thought about related geometries inside there, trying to, for instance, give local explanations to why this cohomology gives you the local Langlands correspondence and so forth. And so I'll say a little bit more about this later. But in fact, these things like aphenoids and these kinds of things, they're basically trying to understand these p-adic groups via some kind of Parahoric level object, some kind of integral level object. And so this is the square that I'd like to fill in today. And not only, oh, there's a bit of a lag. Okay, do you still see my thing going in circles? I see. Okay, great. Today is this box here, and in particular, I want to study this vertical relationship. So between this algebraic side as U and the geometric side, and this will be my bridge here, and this purple thing will be my bridge. So let me first to set up what I mean by this relationship here. I want to give you kind of the simplest possible recipe of a supercuspidal. And so I'll do this for GL2. And so what I can first do is I take what's called a cuspidal representation of GL2FQ. And what does cuspidal mean? It basically means it's not, I mean, in this situation, it literally means this. It doesn't come from a principal series representation. It's the stuff that you don't get from parabolically inducing, easy stuff. So once I have this cuspidal representation, I can actually view it as a representation of this GL2OF, because there's a natural surjection from this GL2OF to this GL2FQ just by sending the uniformizer to 0. And then I'll extend it by center, that's not so important, and then I'll build the representation out of this by compact induction. And so this recipe on the nose gives you a depth 0 supercuspidal. And so how do you get a positive depth representation? Well, the recipe of U says, instead of doing this easy thing here, where I just pull back along this natural surjection, I'm going to supplement with a rather involved algebraic recipe. So it takes together this geometric thing and glues to it some algebraic stuff, and then you get a positive depth object. And so that's what I mean by the algebraic approach here. And what I mean by geometric approach is, well, suppose instead of changing 2, I just change 1. I keep 2 as the easy thing of pulling back, and I put all the hard stuff in 1. So what I want then, I want to see more than just the action of GL2FQ. Maybe I'll want to see, not just the action of GL2 of O mod P, but maybe O mod P squared or O mod P cubed, and so forth. Okay, and so if I did it correctly, the slides will be kind of color-coded, so you'll have key pointers as to which side we're on. Because in the end, what we will need to do is talk about the algebraic side, talk about the geometric side, and talk about this bridge of how to translate between the two sides. So one thing also is that the geometric side is quite far behind the algebraic side. And so that's something to keep in mind. Any adjective that I have is something extra on top of the general construction of U. Okay, and the theme that this bridge will be centered around is the following question. So suppose I have a representation inside a box and I hide it from you. How much do I need to tell you about this representation in order for you to discover what the representation is? Now, of course, the obvious thing is if I told you the character of the representation, then you would know everything. But oftentimes that's pretty complicated. I mean, for example, if you have a representation that comes from some induction, and then a representation that comes from geometry, which is kind of the situation that we are in, how are you supposed to, I mean, the character formula will kind of give some hint as to how you calculated it. It will be algebra bias or geometry bias, and it's probably very hard to compare on the nose that the two formulas are the same. but in any case, I mean, representations have so much structure, right? So it's likely that this representation that I have in this box is determined by a lot less. And so this is what we will think about. Okay, so let's now talk about use construction. I'm going to give you some pictures. And okay, so in this area, oftentimes Parahorics, things like GL2ZP, are denoted by a rectangle like this. And let me, okay, Jessica's laughing, so maybe, yeah, I can see you guys now, so I can respond to body language. So, and the way, okay, so what this picture means is that this central column right here, the central column is some torus that I've picked ahead of time. And so since I've picked this torus ahead of time, I mean, I can now consider roots, something root theoretic, and that's what these vertical things here are. So they're green because roots is like plants. And then depth are these horizontal things. And so I've colored this roughly blue, with light blue being at the top to match with Jessica's epipelagic picture with oceanography. That light blue is where the sunlight hits, and then as you get deeper, you get more mysterious things, and the blue gets darker. Okay. Okay, so, oh, okay, I got confused. Okay, great. So the other thing is that, I mean, the parahoric, what it actually looks like is that it actually should extend arbitrarily far down. However, because we're interested in constructing these supercuspidals, everything is smooth, which means that the non-trivial contribution to a representation is all stops at some finite level. So that's why we can ignore this part. And then we only consider this compact thing. Okay. So let me, okay. So what is U-datum? U-datum is the stuff that you need in order to run use construction. And what you need are three things. You need a depth zero input, you need a sequence of twisted levies, and you need a character for each levy. So this is some data. And the way that this is, and what we will focus on is how to encode this into this picture. And so to these three things, we will assign a subgroup, and this is the subgroup K that came up in Jessica's talk, and it kind of looks like this pyramid thing. And so the sense that I want to give here is the kind of level of involvedness of this algebraic construction, which is you first, from this data, you draw this picture. At the very, very top, you put in this geometric information of this geometric, depth zero input, and then you glue together a representation that's been algebraically constructed on this pyramid. And so glue here, representation theoretically means you tensor them together. Okay. So we have this. So just maybe a small example to keep in mind is if I take GL2, actually there's not so many choices for what your sequence can look like. Either your sequence is just itself, your GL2, or you have a GL1 inside your GL2, so a torus inside your GL2. In GL4, you can get one more step and get a GL1 sitting inside a GL2 sitting inside a GL4, which you could think of it as, I mean, this is your GL1, this is your GL2, and then this is your GL4. So this is another way to write down this picture. And so two special cases that will be important in this talk for pictures of this type will be first the depth zero case. In the depth zero case, everything comes from the geometry. And so the idea is you start with something like what we saw in the simplest recipe. You start with the cuspidal representation of GL2FQ, pull it back, and induce up. And so here, the only non-trivial data is coming in right here, and this stuff, this is geometric. The other thing that, the other example to keep in mind is what I would consider the simplest positive depth example of a supercuspidal. And this looks not so much like a pyramid anymore, because now the sequence is much shorter. It just consists of two things, a torus and your G. And so again, in the GLN case, you can think as this is my torus, and then, yeah. Okay. So this is my algebraic setup. And so so let me tell you about the geometric setup, and then we'll try to compare and see how far off we are with the two data. Ultimately, we want some picture that looks kind of like these rectangles. Okay, so here we see the first important assumption that I will make actually for the rest of the talk, which is this, which is I'm going to select a torus T inside my G, and it has to be a maximal unramified torus. This means that T splits over an unramified extension. So in the GLN case, let's say GL2 even, GL2, let's see, if I have GL2 of some p-adic field, let's even put a QP here, then my maximal torus will look like QP squared. What I am not allowed to take is a ramified extension of QP. That is not allowed for me. And this is an assumption that of course we would ultimately like to get rid of, but as it stands with the geometric setup, this is the limit to our generality. So there's some complicated definition here, but I wanted to put it here in case you are someone who has studied the linguistic varieties before. And if you are, this formula is basically what you would guess for the formula for an analog of a linguistic variety for a parahoric, if you were kind of to shoot blindly. This is based on the first person to come out with a definition of this type was Lustig in 15 years ago. And what Lustig studied was the special case where this quotient right here looks like it's something like GLN of a finite ring, something like this. And what Stasinski did a few years later was generalize Lustig's setup so that you didn't have to have something equal characteristic inside. You could have something mixed characteristic. And then, together with Ivanov, we generalize this so that you can put in any parahoric that arises from this unramified setup. Okay, so this is some scheme over FQ bar, and it has basically all the properties you'd want it to, like, that you desire of a scheme. Some comments here is that if you take R equals to 0, this is exactly the same as a classical delinguistic variety. And the second thing that we want is, well, we're looking for representations. So this means that we need to find some group actions somewhere. And so where are our group actions? Well, the parahoric, the sigma fixed points of the parahoric acts on the left, because if I put a gamma here, for instance, then it will pull out in the middle, and it will it will just vanish from this defining equation. So I have a left action by the sigma fixed points of my parahoric, and I have a right action by kind of like the integral part of a torus. And what this means is that if I now take the cohomology of XR, I then get a vector space that has an action by my parahoric and an action by this torus. And whenever I have this kind of situation where when you have two commuting group actions, what you can do is parameterize representations of one group via representations of the other group. And typically what you want to do is the parameterizing set should be the easier group. And so that's our T over here. That's our easier group. Okay, and so that's what this sentence is here. So given any character of this T over here, I can look at the subspace of the cohomology where the T acts by that particular character. And now this resulting thing is a representation of my Parahoric. Okay, and so what we're interested in, right, so this kind of picture where we take a torus and then outspits a representation of a Parahoric will occur in other places as well. So let me give you some example, an example of what this XR looks like so you have something to hold on to. So let's take the case of GL2, and I'll just keep it in equal characteristic setting, but mixed characteristic setting is essentially the same. In this equal characteristic setting, what I'm allowed to do is take this FQ squared Laurent series over FQ squared, the multiplicative group of this. And in this context, the Parahoric that arises is just GL2 of the ring of integers. And we saw in Jessica's talk that there was this moist Prasad filtration, and this is some sequence of smaller and smaller subgroups of my original Parahoric. And in this setting, these things are just congruent subgroups of GL2. So things that are like, I am going to take the collection of all matrices that are equal to 1 up to some power, like up to T squared or modulo T cubed, etc. And so when you take this quotient, all you get is GL2 over a finite ring. In this case, X0 is a disjoint union of some number of copies of the so-called Drinfeld curve. And the Drinfeld curve is something that appears in many, many different contexts. So, and one way to write the Drinfeld curve is by this equation. You might be more familiar with this equation. But these are isomorphic curves over FQ to the 4. Okay, so how do we, so what are the higher ones? I mean, what's X1, for instance? Well, first, what I can observe is that this X0 to the Q plus 1 minus Y0 to the Q plus 1 is just the determinant of this matrix. And what I will do to get X1 is I'm just going to beef up every coordinate by an additional power of T. This is some matrix in some finite ring, and I will take this X1 now is just the affine variety cut out by the equations, the two equations that come out of equating this determinant to 1 modulo T squared. And in fact, these are exactly the varieties that I will use in order to get this geometric construction, replacing this step 1 that we saw in an earlier slide. Okay, so these XRs actually have appeared in have appeared in various contexts, and so I'd like to say something about that. So they've appeared in aphenoids in the Lubin Tate tower. I mean, not just X0, but also X1, which, for instance, gives a local geometric explanation as to why, I mean, where you're finding higher depth supercuspidals inside the cohomology. But aside from this, these things are also appear in kind of in other geometric constructions. So there's a geometric construction of Lustig that happened in that was conjectured in 1979, and this was actually kind of forgotten for some time. And what Lustig did was he wrote down an analog of a Deligne-Lustig variety, where instead of FQ everywhere, you just replaced it with a p-adic field, and he conjectured that this should have good geometric structure. Now this this has been a conjecture for some time, and only in special cases do we actually know all that much about the situation. So in the division algebra case, Lustig gave it this object a geometric structure in his original paper, and this was made precise in 2012, and then I calculated the cohomology later. And this is also the description of these this kind of loop Deligne-Lustig object is partially understood for other inner forms of GLN as well, and that's work of myself and Ivanov. And in all of these computations, I mean, this loop Deligne-Lustig object is something massive. It's extremely infinite dimensional, and the way all of these calculations go is you have this massive infinite dimensional thing. I'm going to slice it up into these finite dimensional pieces, and then I'm going to study the cohomology of these finite dimensional pieces. And these finite dimensional pieces are exactly these XRs. So now very recently, Ivanov gave these loop Deligne-Lustig varieties a very natural geometric structure using perfectoid technology. And so now this means that we don't have to write this word loop Deligne-Lustig sets anymore. We can actually at least loosely call them varieties. In general, it's not clear what the relation is to XR. The relation to XR that we know of now is only in the GLN setting. So all of these things are in GLN. And let me mention one other place that these have appeared, and I guess are to appear, is a conjecture of Laurent Fargue. What Fargue conjectures is that there should be some kind of Deligne-Lustig stack, some fancier version of these things earlier in this table on the Fargue-Fontaine curve, and what this should do is basically bundle together everything in the second bullet point. So all the inner forms, all the geometries for the inner form should be bundled together, and so this object should, for instance, know about Jacquet-Langlands transfers and this thing all in one object. And this, as I understand it, it's now known that it reduces. You see these loop Deligne-Lustig varieties for the GL2 case, and this is work in progress by Fargue, Imai, and Geising. Okay, so let me tell you about what we know about these XRs. And the situation is that, I mean, we're far from knowing everything. So in fact, the only case that we know everything is in the division algebra setting. And in the division algebra setting, what ends up happening is something that's more simple than what you expect to happen in general. And so what happens? Well, for any character theta, it turns out that these cohomology groups are irreducible and also concentrated in a single degree. If you have some experience with Deligne-Lustig varieties, what happens there is that oftentimes whenever you have concentration in a single degree, it's always happening in the middle degree. But actually that's not the case for these high depth versions. You get concentration in a single degree, and that degree can change basically depending on the complicatedness of your theta. For GLN, we know that this is always irreducible, but we don't know whether it's concentrated in a single degree. We do expect it in some situations, but so already we lose this concentration in a single degree. And then if we are to drop the assumption of these specific groups, G is the division algebra, G is GLN, what do we know in general? Well, in general, we have to make an additional assumption. Only when theta is very generic can we say that this cohomology yields an irreducible representation. So how are we supposed to go about comparing this geometric stuff with the algebraic stuff? Well, what we know is, I mean, I claim that we know most things about GLN and the division algebra setting. So what happened here? How did we know what representations we were getting at there? And the way we knew that was via a result of NER in 1992. And what NER's result says is that the supercuspidal representations of GLN are determined by their character on a very small part of the group, the so-called very regular elements. Once you know the character on very regular elements, and the character is very simple there, then actually you know everything. And this result has been used in the GLN local Langlands world many times to basically figure out what the relationship is between different constructions that people have of supercuspidals of GLN. And so, in fact, this is the result that is used in Theorem 1 and Theorem 2 in order to relate this to the local Langlands correspondence for GLN. Okay. And so, since the thing that we want to figure out is if we're to do a comparison outside of GLN, we need some kind of result of this type, and that's exactly the main theorem of today, which is if I have a representation pi, and I know it's irreducible, and I know that on this kind of very small, very special class of very regular elements, the character agrees with this geometric guide that I've constructed, then as long as my Q is big enough, I know that that this pi is determined by this character formula on this very small piece. Okay. So some comments about this. So one thing is that when we talk about supercuspidal representations, the torus that comes up all the time isn't an arbitrary torus. It has to be an elliptic torus. That's kind of in the dictionary. But this result here, I mean, the geometric construction works outside of just elliptic tori. Yes, you always need this your torus to be unramified, but you can do non-elliptic tori as well. So in particular, what this is saying is that even for representations that, for instance, arise in more elementary ways, like principal series representations, those representations are determined by their character on this very special class of very regular elements. And so, I mean, that seems like a really elementary statement with the principal series representation. But really, our proof genuinely uses the geometry of XR and a kind of character formula for XR that comes from an analog of green functions, which come up in Deleuze's theory. Okay, so this is our bridge. And what we need to understand now is how to use this bridge to connect the algebraic picture with the geometric picture. And so at present, if you remember several slides ago, what we had was this kind of pyramid. And what we know is that you can construct a representation, rho k, on this pyramid. On the other hand, this geometry is on this geometric thing has an action of the entire parahoric. So it's a representation of the entire rectangle. So, I mean, the left-hand side is smaller than the right-hand side, but actually this is not so major. You can just induce the left-hand one to get a representation of the whole rectangle. The more serious thing is that on the left-hand side, the U datum that we used, our initial datum that we used to construct this pyramid was this collection of three things, right? Depth zero input, these GIs, and these characters on these GIs. And on the geometry side, on the other hand, all I have is a character of a torus. So, I mean, what's going on here? How do I reconcile these two things? How do I guess what representation I'm getting on the algebraic side when I take this cohomology here? But now we're in luck. There's something, so to resolve the issue of the pyramid versus the rectangle, I will just induce this row K, and I will call this row K tau. So the U representation is now called tau. And inside this picture of supercuspidals, there's kind of this regular locus that's more well behaved. And this regular locus is based on, is an adjective that describes what kind of depth zero datum you feed in. And what and this terminology was coined by Tasho Khalifa. And what Tasho proved was that there's a bijection between these regular U datum up to, equivalence classes of these regular U datum. There's a bijection between this data and pairs T comma theta. So that's great, because now we're seeing this T comma theta that we saw on the geometry side, also on the algebra side. And so I'm going to call this diagonal map the map that goes from T theta to tau of T theta. Okay. So just a comment is that in the toral setting, which toral setting, remember that's this picture right here. This parametrization is due to Adler in 1998, and use construction is largely inspired by this construction of Adler. Okay, so now there's a natural guess. Now my algebraic side feeds in a T comma theta and spits out a tau. My geometric side feeds in a T comma theta and spits out this cohomology group. The question is, are they the same? And the spoiler alert is, turns out no in general. Okay, so then what's the deal? What's our hope? Maybe we can figure out what our hope is. Well, this is our geometric construction, right? And if I look at the T equals to, if I look at the R equals to 0 case, then by definition, this tau that arises in use construction is exactly the same as the one that arises in the geometry, just by definition. Because remember, the depth zero input in use construction is a geometric input. And R equals 0 means that there's no further input. It's just the geometric part. And so what it turns out from is that this correspondence here that goes from T theta to this cohomology when R equals 0 preserves something called stability. And what does stability mean? Well, stability is something that is one of the many properties that one expects of an L packet of supercuspidal representations. And basically what it means is the following. So if you just have a single representation pi, say of GLN QP, then the character will be constant on conjugacy classes, on rational conjugacy classes, on GL2QP conjugacy classes. But it's probably not stable on, I guess for GL2 it is, but it's probably not the case that a representation will also, a character will also be constant on GL2QP bar conjugacy classes. And that's the meaning of this stable. So we say that a packet is stable, a set of representations is stable if you take the sum of all of these characters, and that sum gives you a function that's constant on stable conjugacy classes. Now this notion of stability has an analogous notion on the other side. On the T comma theta side, what I can consider is all translates of T comma theta under the F bar points of your algebraic group. And so now this gives me some finite set of T thetas, and I can attach to all of these the corresponding depth zero representations, and it turns out that stable data on the left will go to stable data on the right. And this was proved independently by Debacker Reader and also Kazan Varshavsky. Okay, so question, for R bigger than 0, does our geometric thing over here preserve stability? Right, the moment R is bigger than 0, this tau is not obviously. It's difficult to compare these two now because we have have to mix algebraic and geometric data. Okay, and so the plot twist that has already been spoiled by a previous one is that in general, it's the algebraic recipe from tau, t theta to tau of t theta does not preserve stability. And so, well, oh no, but maybe not so oh no, because what we had a sense of from Jessica's talk is that there's a ±1 that gives lots of people a lot of headache. And there's a ±1 here that also gives a lot of people a lot of headache. And it turns out that if you introduce this a character here, this is a quadratic character, then this assignment does preserve stability. And this was due to this was proved to Debacker-Spice in and published in 2018. In more generality for this entire regular locus, Tasho Kalitha defined an epsilon that's expected to give stability, and my understanding is that at present this is not quite proved. And so this toral setting is the limit to which we know. Okay. So now what we have is we have our geometric construction that takes in t theta and spits out some cohomology group. And we also have this t theta that spits out either a tau of t theta or a tau of t epsilon theta, depending on whether or not you want to take this twist. And so what we want to know is, well, which one, or maybe neither, is the geometric one realizing, this twisted thing or this untwisted thing. Of course, we would prefer if it's the twisted one. We want the recipe to preserve stability. And so let me tell you how we prove this then. So if we go back to, this is now some time ago. If we go back to this theorem here, our bridge theorem, what we need to know is, this pi now is going to be my tau. I want to find a tau whose character is equal to this right-hand side on this very small locus of very special elements. But this means that I need some kind of character formula for tau. Luckily, we do have that, though not in exactly the form that we require. And so there's Adler and Spice wrote down character formulas for these tau, and actually the character formula is very general, so it's not just for these elements. I think it's essentially for all elements. And what we do is we rephrase this on our very special collection of very regular elements, and we, in order to make it look like the character formulas that arise from the geometric context. These, right. So once we've done this, then combining these two, we just need to apply theorem 4, and what turns out to be the case is that this, we do in fact see this epsilon here over already. And so in other words, whereas somehow this epsilon was discovered somewhat later in the algebraic setting, the geometry actually already knew about the epsilon. And in fact, on the geometric side, it doesn't know how to not know about epsilon. Okay. So a further comment that I would like to say is something about this here. Okay. So this is some number. This is an integer. And this integer depends on several things, on t and theta. And this integer is something that's defined on the algebraic side. Now, why do we have this thing? How can it be that a representation can be equal to minus another representation? Well, the reason is that this cohomology group, this is an alternating sum of cohomology groups. So you get like plus in even degrees, minus in odd degrees. So the right-hand side will only be a genuine representation if you have everything in even degrees, or you have something in odd degree, but then actually you put a minus sign in front. And so what this is, what what this isomorphism is saying is that this algebraically given integer n of t theta actually has some geometric meaning as well, right? If this guy is irreducible, then it means that, I mean, you might have some cancellation, but your final remaining representation in, you know, plus minus, has to appear in either an even degree or an odd cohomological degree. And the parity of that, even or odd, must exactly match the parity of this n of t theta. So what do we see now? Well, this was the picture that we had before. We started with these t thetas. We twisted by this epsilon, and then went over to the supercuspidal side. And what we found was that this composition then preserves stability. In Jessica's talk, she mentioned that there's another epsilon, I mean, actually a very closely related epsilon, that's defined on this K. And so we can actually put this all into a picture. So this epsilon over here, instead of just twisting on the character, what I could do is twist on the row K, and this is the same operation. Okay, and so what this result here is telling us is that the geometry is realizing the diagonal of this map here. So now we had some algebraic construction, some geometric construction, and we see that the link between these two is some twist by a quadratic character. And that quadratic character is exactly the same quadratic character that's appeared in several contexts in order to fix things like stability. Okay. So as a corollary, what we see from all of this is that because on the algebraic side, we already know what the L packets should look like and what the Langlands parameters should look like. This means that we can just translate this and put in our geometric thing. So if you and maybe a slight advantage of this is now it's easy to write down exactly, like it's easy to show, you know, like here is my representation space. It is the cohomology of this thing. On the other hand, it's more mysterious in some ways, right? You don't have an explicit algebraic construction. So there's, right. And so the statement here now is that if theta is sufficiently generic, so we're in this toral setting, which is the limit to which we know stability, then the L packet corresponding to this Langlands parameter, this Langlands parameter was defined by Tacho, is exactly this set, which is I take the compact induction of all of these geometrically arising representations coming from the cohomology of this XR, and I vary the data of this T prime and this theta prime amongst the members of a stable conjugacy class of the original T theta. And this is my geometric L packet now. Okay, and yeah, so far in this talk, basically what we've seen is that once we have this bridge, we know things about geometry because we can just take it from the algebraic side. And I hope that in this bridge, we will also eventually be able to take some the geometry side and transport it over to the algebraic side. So one example of this is on the geometric side, the character formula for these representations looks very different because it comes from like flag variety geometry. And that then gives an identity of character identities for the same representation, which wasn't at all clear. I mean, at least I don't know how to by hand manipulate one formula into the next formula. Okay, and I'll stop there. Yeah, thank you very much.
Let us thank Charlotte for a beautiful talk, and we're opening for questions. There is a question from Jessica. Please go ahead.
Hi, thanks. Is there any hope to go beyond the unramified case?
I think you should be able to go to maximally unramified case.
I mean, you assume that your torus splits over an unramified extension. Is there any hope to work with something that only splits over a tamely ramified extension?
Right. So I think one should be able to, like, I'm quite sure one can do the maximally unramified maximal torus case. So this is maximally unramified maximal torus is the setting of regular supercuspidal. So this, I think, should be able to be done. I have some vague ideas for like ramified tori, for instance, where it's not maximally unramified. But kind of like you wouldn't get the whole, somehow the current idea in my head, you wouldn't get the entire GX0 action. You would get some piece of the GX0 action that you would then later induce. I mean, maybe that's not so bad, but so I think there's some vague hope, but I don't know.
Thanks.
Any other questions?
Oh, one very small question. So in your theorem 5, how do you determine the R on the right-hand side?
Oh yeah, great. So the R is determined by the theta. So your theta is a smooth character, and so at some point you'll have some congruent subgroup on which that character is trivial, and so you just need to pick an R that's big enough that you know. So that capture all the non-trivial stuff. So you just need it to factor through that finite quotient.
Okay. Thank you.
I don't see any more questions, so maybe we can just thank Charlotte again.
Tony asked.
Sorry. Please go ahead. I don't see.
No, yeah, I guess I was just wondering if you can relate your construction to like Genesee Lefort or maybe even Shelto thing.
I haven't really thought about it. Yeah, so like you want to know whether, like it appears as like a fiber or something like that.
Yeah, I guess if they're compatible.
Yeah, I don't know. But for instance, if you knew some mild character formulas about the Genesee Lefort or representations that come out of that, then you could at least use the bridge.
Yeah, I think that's the kind of thing we don't know, but since their thing is also geometric, maybe somehow the geometric spaces are related.
Right, yeah, then that's a more direct approach, yeah. Yeah, I don't know. I haven't thought about it.
Okay, thanks.
Sorry, I just wait a little longer since I have trouble seeing whether people raise their hand. Well, if not, let us thank Charlotte again for the talk.
Thank you.